structure study guide to help you go through. So here is a structured study guide to help you go through the introductory lecture on elliptic curves by Professor Álvaro Lozano-Robledo. Motivation: the hierarchy of Diophantine equations. So here I was going through this lecture by Professor Álvaro Lozano-Robledo, and then he decided to take help. I went through about 40 minutes. I jumped through the video due to this location, but thought about there is no point going through without understanding anything, so I decided to take it from the Google's AI studio. I asked about asking help to help me follow through the lecture. So here is the structure study guide to help follow through the introductory lecture by Professor Álvaro Lozano-Robledo. The hierarchy of Diophantine equations. So the motivation part contains Diophantine equations. So what are Diophantine equations? That's a question. If a polynomial equation with integer coefficients where we search for rational or integer solutions. Is a polynomial equation with integer coefficients where we search for rational or integer solutions. Okay, Q or Z. To understand why elliptic curves are special, consider how solving Diophantine equation increases in difficulty by degree and number of variables. Okay, to understand why elliptic curves are special, consider how solving Diophantine equations increases in difficulty. Okay, like to solve the equation, then the difficulty increases by degree and number of variables. So if we have one variable and geometric shape like points, solvable divisibility theory, rational root theorem. Okay. If we have two variables, degree 1 like straight lines x plus by equals c, solvable greatest common divisor GCD and Euclidean algorithm. Greatest common divisors and Euclidean algorithm. Okay, if we have two variables and degree is 2, like if we have conics like circles, ellipses or hyperbolas, then that's also solvable. Hasse-Minkowski local to global principles and other approaches like stereographic projections to parameterize all points on point is found. Okay, so if we have on point, then we can use the stereographic projection to parameterize all points on point is found. Okay, and now comes the part where we have two variables and we have 3 as degree cubic curves. Okay, the frontier. Classical methods fail here. There is no general algorithm to find all rational points. Okay, now what is an elliptic curve? Definition: an elliptic curve E, we are calling it E, or a field F, is a there is no, so non-singular means like there is no singularity, or like, so it's like spike. Yeah, so there is no spike anywhere in the surface or the field or the space. There is, yeah, non-singular. If we have any spike, then they're singular. So non-singular means is small. Then there is projective cubic curve of genus 1. Projective cubic curve of genus 1. Okay, an elliptic curve E over a field F is a smooth projective cubic curve of genus 1. So genus 1, that's an important terminology, and we will go through that when you ask about it. Okay, so let's follow through. So yeah, to move ahead, we need to sometimes ignore some details and just follow through. Otherwise, we will be stuck and won't make any progress. So, containing at least one specified base point defined over F, often denoted as at least one specified base point defined over F, often denoted as okay, the point at infinity. I don't recall how to call the symbol, but yeah, it's big O. I think that it looks like O. Maybe some Greek character, Greek letter. Okay. So often denoted as O, the point at infinity. So there's some interesting details. We consider a point at infinity. So we have 3 points on the curve, and another one we consider that to be at the infinity. Okay. Containing at least one specified base point defined over F. Containing at least one specified base point defined over F. Weierstrass form. By the Riemann-Roch theorem, every elliptic curve can be written in the generalized Weierstrass equation. Okay, so it's a generalized form of an elliptic curve equation, and when the characteristic of F is not 2 or 3. Okay, so there is another important term, characteristic. There is characteristic 0, characteristic P, characteristic 1, if I recall correctly. So there's a thing in mathematics. So I forgot the exact definition, but sometimes it's a simple definition. Yeah, but I don't remember. I can't remember it. What to say? Like, yeah. I will try to like grasp the internal of what it means to be a characteristic P or characteristic 0, and go through the passage, and again after some days or a few days or a month later, if I again encounter the characteristic, this keyword, I will completely forget like what that meant previously, or what I learned previously about this. So this keeps happening, so nothing to worry about. Yeah, characteristic of F is not 2 or 3, then we can simplify the equation to y squared equal to x cube plus x plus b. It's more commonly used than the larger equation. Okay, so there is the term characteristic, and another one is the genus one. Okay, now key examples and applications. The congruent number problem. Question: which natural numbers n can be okay, these are some examples where elliptic curve theory appears or just pop up. Which natural numbers n can be the area of a right angle triangle with rational sides ABC. A number n is congruent if and only if the elliptic curve y square equal x cube minus n squared x has a rational point with y not equal 0. Okay, that went over my head. A number n is congruent if and only if the elliptic curve y square equal x cube minus n squared x has a rational point with y equals. Yeah? ডোমিনোস এখন অর্ডার দিবা? এখন 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 কি ডেলিভারি দিতে পারবে? আর ইউ শিওর? যদি ডেলিভারি দিয়ে যায় ওই ইয়ে করো টাকা। ঠিক আছে, এখন তো ক্যাশ করা লাগবে। ক্যাশ করা তো যাচ্ছে না মনে হয়। তোমার কাছে ক্যাশ আছে না? ঠিক আছে তাহলে ওকে। হ্যাঁ ঠিক আছে ওকে। কি অর্ডার দিছো তুমি? গার্লিক ব্রেড চিকেন টাকো। হ্যাঁ ঠিক আছে মনে হচ্ছে। হ্যাঁ ওকে। এই ঠিক অ্যাড্রেস ঠিক আছে। Okay, that was something. Okay, let's go. Farmer's last theorem proved by Andrew Wiles using elliptic curves via Frey curves. Proved by Andrew Wiles using elliptic curves via the Frey curves. Y square equal x. We take products x into x minus a per n into x plus b per n, and modularity theorem. Okay, that's important. Cryptography. Elliptic curve cryptography relies on the difficulty of the discrete logarithm problem on elliptic curve group structures. Geometric group law. Chord and tangent method. Okay, rational points on an elliptic curve. Rational points on an elliptic curve form an abelian group under a geometric operation. Rational points on an elliptic curve. Okay, so the points on an elliptic curve, okay, rational points, they form an abelian group under a abelian group means commutative group under a geometric operation. Okay, so what's the operation? Okay, adding two distinct points. Like if we take 2 points on the curve P and Q and we add them by like line through them through P and Q. We take 2 points P and Q, we draw a line through P and Q, then it interacts the cubic curve at a third point R. So the line intersects the cubic curve at a third point. So the curve gets intersected at another point R. And so if you have seen elliptic curve before, there is a okay, we take a reflect, so we reflect R across the axis of symmetry to grade p plus q axis. So we take the, like, if we are taking some point r on the above the, like, x-axis, then the reflect of r we will take, that will be the reflection on the downside of the x-axis. Okay. So we take a so we draw a line. I think that's clear. Exact opposite point, and on the opposite side of the x-axis, the x-axis, like the mirror image. Yeah, mirror reflection. You know what? You know all this. So draw the tangent line at P, doubling a point. To P. Okay. Tangent line at P. Okay, we draw a tangent line at P. Okay. Tangent at P. This is the curve, so that will be 90 degree. To specify the direction here, because a tangent over a curve, yeah, that's always gonna be, that's unique. Yeah, no disambiguity here. Okay, it intersects the curve at a second point R. We take a tangent line at P that intersects the curve at a second point R. We take the reflection of our symmetry axis and we get 2P. Okay, that's not something I remember, so yeah, that's new to me. কোনটা? ওইটাই মানে ওদের হচ্ছে অর্ডার তো হইছে না। Understand some parts of it, but don't understand the whole thing. Okay, so finally generated. It's confusing, but other than that, group of rational points and finitely generated abelian. By the structure theorem for finitely generated abelian group. By the structure theorem for finitely generated abelian groups, a cube decomposes as structure theorem for finitely generated abelian groups. EQ decomposes conjunction. I'm not sure what that means here. Jet R dimensions. Torsion sample. So rational points EQ. We are taking the torsion subgroup of EQ, the finite group of points with finite order. Measures 1937 over Q. There are only 15 possible torsion subgroup structures. Yeah, there are some like things like this, like this one. Over Q, there are only 15 possible torsion subgroup structures. Say Q is infinite, and we are getting that there is only 15 possible torsion subgroup structure. So yeah, on the on side you have an infinite something, like Q, and on the other side you get something that's finite, like 15 possible torsion subgroup structures. I noticed something for the SLN, special linear group or general linear group. They have something like this, like you can count something general group, but if you the matrix comes down to so a number of finite curves maybe. Often like finite objects some structure inside the gives triple Frankel points of infinite order. Measures how many independent points of infinite order generate the rest of the rational points. How many independent points of infinite order generate the rest of the rational points? Open problem. Can the rank R be arbitrarily large? Current record. Norm LQ is yeah, yeah. Notice here. That's the same thing again. The conjecture suggests that ranks over Q might actually be bounded. Yeah, that's maybe like countable something or finite something. So yeah, Q might be like infinite or very big, but uncountable. But the ranks over Q that might actually be bounded or countable or like finite something. So how to compute the rank? Determine the rank R of an elliptic curve is rank of an Birch and Sonneton-Dyer conjecture. Analytically, Birch-Sonneton-Dyer conjecture, the PhD conjecture, yeah, is predicted to equal the order of vanishing of the Hesse L function. Yeah, there's another thing, L function. It is equal and unproved in general one of the Clay millennium problems worth $1,000,000. Okay. The rank R is predicted to equal the order of vanishing order of vanishing of the Hasse-Weil function. Algebraically, p-descent methods use Selman groups and the Tate-Shafarevich group to bound or compute the rank. The algorithm is guaranteed to terminate provided SHA is finite. Okay.